Welcome to G Fun Facts Online, where we unpack the biggest ideas in science. Today, we're talking about a puzzle that has stumped the greatest minds in physics and mathematics for over a century. Imagine trying to write a single perfect recipe that explains everything in the universe, from the zipping of a single atom to the swirling of a hurricane. That, in a nutshell, is the quest for a unified theory of physics, and a major piece of that puzzle might have just been solved. Back in the year 1900, a legendary mathematician named David Hilbert laid out a list of 23 problems he believed would define the future of math. The sixth problem on his list was a monster. He essentially challenged the world to build physics from the ground up, starting with a handful of fundamental truths, or axioms, just like building all of geometry from a few basic rules. A key part of his challenge was to mathematically connect two very different worlds. The microscopic world of individual particles, each following its own simple rules, and the macroscopic world we see, like the smooth, continuous flow of water in a river or air flowing over a wing. For 125 years, that gap remained. How do you get from a quadrillion tiny bouncing balls to the elegant equations that describe a fluid? Well, in early 2025, a team of mathematicians made a monumental claim. Yu Deng, Zahor Hani, and Xiao Ma released a paper announcing that they had finally built that bridge. They claimed to have rigorously derived the fundamental equations of fluid mechanics, the very math we use to predict weather and design airplanes, directly from the basic laws of motion governing tiny colliding particles. So how did they do it? Think of it as a two-step process. The first step was to get from the chaos of individual particles, each governed by Newton's laws, to something more manageable. They used a concept called the Boltzmann equation, which is a statistical description of a huge gas of particles. It doesn't track every single particle, but it describes their collective behavior. They rigorously showed how this statistical rulebook emerges when you imagine an infinite number of impossibly tiny particles colliding. The second step was to go from that statistical rulebook to the equations of fluid dynamics, like the famous Navier-Stokes equations. This happens when you consider a limit, where the particles are colliding so frequently that their collective motion looks like a smooth, continuous flow. Now, other brilliant people had tried this before, but they could only make the math work for incredibly short periods of time, a tiny fraction of a second. That's not very useful for describing a storm that lasts for days. The real breakthrough from Deng, Hani, and Ma is that they claim their derivation holds for long periods. They developed new mathematical tools to tame the immense complexity of tracking trillions of collisions over time, proving the connection holds for as long as the fluid itself exists. If their work stands up to scrutiny from other experts, this is a historic achievement. It provides a rock-solid mathematical foundation for a cornerstone of physics. The practical implications are huge. It could lead to more reliable climate models, better weather forecasts, and more efficient designs for cars, planes, and engines. By understanding the fundamental why behind the fluid equations, we can make our simulations of the real world much more accurate. But let's pump the brakes just a little. It's crucial to understand that this work is currently a preprint, meaning it's been shared with the scientific community but hasn't yet completed the rigorous peer review process where other experts try to find any flaws. And while it's a monumental step, it doesn't solve all of Hilbert's sixth problem. The grander challenge of axiomatizing all of physics, especially reconciling the twin pillars of quantum mechanics and general relativity, is still a distant frontier. This work doesn't give us a theory of everything. What it does do is reinvigorate a 125-year-old quest. It's a stunning confirmation of the deep and powerful connection between abstract mathematics and the physical world. It shows us that even the most daunting scientific challenges can yield to persistence and ingenuity. The journey to fully understand the mathematical blueprint of our universe is far from over, but thanks to this incredible work, we may have just taken one of our biggest steps yet.